So far we have had a look at what is heteroscedasticity. Heteroscedasticity is when the error term ui or the disturbance term ui in our population regression function is not having constant variance. So if expectation of ui square is equal to sigma I square, we call it an equation which represents heteroscedasticity. We also had a look at what happens or what are the consequences of heteroscedasticity. We had a look at different tests, formal as well as informal, for detecting heteroscedasticity. And now we come to the final part where we look at remedial measures. What can be done and how can we estimate a sample regression function which will help us locate the population regression function in the presence of heteroscedasticity. So as you can see in the slide, there can be two possible alternatives. In the first alternative, our sigma I square is already known to us. This could happen if we have had earlier empirical studies which give us an idea about the value of sigma I square, or you have very solid theoretical foundation which tells us or gives us a fair idea about the value of sigma I square. In such a situation, we would apply the weighted least squares method, which we have already discussed in the earlier lectures, where we'll transform the original regression model by dividing each term of the original model by sigma I and then running the regression there. So in the transformed model, like we had discussed earlier, the error term of the transformed model is now homoscedastic, and in that case it will be equal to 1. Okay, constant variance equal to 1. So that's one of the methods. But now what if sigma I square is not known? And generally, more often, the population sigma I square is not known. In that case, one of the most popular methods is the White's heteroscedasticity consistent variances and standard errors method. So White has shown that these estimates can be found such that asymptotically, that is, in the case of large samples, they'll give you a decent and reliable inference regarding the true parameter values. Now, we are not going into the exact methodology and procedure of the White's arriving at White's heteroscedasticity consistent variances, because it is very involved. So you just need to remember the name of it. Mostly these days we run regressions using statistical packages of various sorts. So most of these statistical packages have an option where you can run the White's heteroscedasticity consistent variances to be calculated. It's called the White's process. So you just have to tick or check the box which says White's process, and then you will get these heteroscedasticity consistent variances in the final output. Right? So just remember the name for your exam purposes. And then other than that, because White's heteroscedasticity process or White's process is more valid in the case of large samples, even that might not be preferable. The other option when the population sigma I square is not known is to do a transformation of the original regression model such that you get homoscedastic variances, right? This method of transformation is arrived upon based on your assumption that you have about the pattern of heteroscedasticity. So we'll discuss 4 to 5 different assumptions and what is the transformation to be carried out if that assumption holds true. We are referring to the simplest 2-variable model, yi is equal to beta 1 plus beta 2 xi plus ui. And we are saying that in this case the variance of the term ui is not homoscedastic, it's not constant. And so based on our assumption about the pattern of heteroscedasticity, we transform it. The first assumption that we discuss is suppose we have prior knowledge or prior suspicion that the error variance is proportional to xi square, right? That means, as you can see, the expectation of ui square will give you the variance is equal to sigma square times xi square. So it is proportional, directly proportional to xi square. In that case, you can transform the original regression model by dividing each term by xi. As you see here, so you got yi by xi is equal to beta 1 by xi plus beta 2 plus ui by xi. Now this transformed error term, we are calling it vi, right? And if you notice on the right hand side over here, we show that the variance of this transformed error term is equal to sigma square, right? Basically you can take 1 by xi square outside the expectation symbol because it is stochastic, sorry, it is non-stochastic or non-random. Okay, you might have learned these properties of expectations and variances in your statistics classes last year. So all you need to remember is, in this transformed variable, this transformed error term vi is homoscedastic. And when do you use this transformation? When you have an idea that the pattern of heteroscedasticity, that is the variance of the error term, is proportional to xi square. Okay. Now, if you have an idea that the variance of the error term is proportional to in the last case it is proportional to xi square. Okay. Now suppose in the second case, suppose you have an idea that the variance of the error term is proportional to xi, that is e of ui square is equal to sigma square times xi. In that case, you will transform the original regression model by dividing each term by root under xi. So as you can see, this will be your regression model that you should run. This is your transformed regression model, and as you can see, both beta 1 and beta 2 have variables attached to it. So there is no intercept term in this model. So you should remember, if you ever have to run this kind of transformed regression on a statistical package, you will have to use regression through the origin option. Okay, whenever you are running a model without the intercept term, it is called a regression through the origin model to estimate beta 1 and beta 2. Okay. And in the previous case, I missed out this point. If you notice over here, you do have an intercept term, but the intercept term is the slope in the original model, and the slope in the transformed model is actually the intercept in the original model. All right, but of course that is just, I'm just pointing out to you, the statistical package will do all of this. Just understand the logic of the transformation and ensure that you understand that in the transformed model the error term is homoscedastic, that is, its variance is constant. So even in this model it can be shown that this error term vi in the transformed model is homoscedastic. Another assumption that you can make about the pattern of heteroscedasticity is that the variance of the error term is proportional to the square of the mean value of y. So that is, for every corresponding to every xi value, you can estimate the mean yi. And you're saying that the spread of the error term around this mean value is proportional to the square of it. Now you know that the expectation of yi is nothing but, or the mean value of yi is nothing but beta 1 plus beta 2 xi of the population regression function. So you can transform it by dividing it by expectation of yi, or the mean yi, population yi, right? And the error term of the transformed model again is homoscedastic. But the problem is that we do not really know the population beta 1 and beta 2. These are unknown. So what you can do is, step 1, run the original OLS regression as yi hat is equal to beta 1 hat plus beta 2 hat xi plus ui, and arrive at values of beta 1 hat and beta 2 hat, and then calculate yi hat. Remember, we always say that the best estimator of expectation of yi is equal to the yi hat, the estimated yi hat value. And so you can use this estimated yi hat to divide the entire original regression model. So in step 2, we run the transformation where yi is divided by yi hat, beta 1 is divided by yi hat, beta 2 is xi is divided by yi hat, and the error term ui is divided by yi hat. Once again, the reason we are using yi hat is because it is the best estimator that we have of the original expectation of yi. So the authors mentioned that although yi hat is not exactly expectation of yi, they are still consistent estimators. That is, as the sample size increases, the estimated yi hat values do converge to the true mean value of yi. So once again, practically speaking, this transformation will be successful if your sample size is reasonably large. Another possibility, another method of reducing the heteroscedasticity is to carry out a log transformation. So your original regression function is like this: yi equals to beta 1 plus beta 2 xi plus ui. Transform it, do a log transformation on both sides. So you will have log yi is equal to log beta 1 plus beta 2 times log xi plus ui, right? This log transformation reduces heteroscedasticity quite a bit. This is because log transformation changes the scales on which the variables are mentioned. So to roughly make you understand, have a look at this. If I talk about the powers of 10, 10 to the power 0, 10 to the power 1, 10 to the power 2, and 10 to the power 3. So basically, if your variable is increasing as 10, 100, 1000, 10,000, as you can see, the rate of increase or the scale of increase is quite high. Now, if I do a log transformation of these numbers, you can see the same increase as 1, 2, 3, and 4. Remember, log 100 base 10 will be equal to 2, right? So as you can see, 10, 100, 1000, 10,000, that scale of numbers are being changed to 1, 2, 3, 4 scale. So the scale has become much more reduced. The difference between these numbers, consecutive numbers, has reduced to a great degree when you do a log transformation, Okay, so from 10 to 100 to 1000, if you look at the change in the absolute numbers, it's very large. But if you do a log transformation, the change in these same numbers has become on a much more smaller scale. It's become almost linear, 1, 2, 3, 4. Right? Because I have taken log of 10 is 1, log of 100 is 2, log of 1000 base 10 is 3, log of 10,000 is 4, and so on. So as you can see, when the scale reduces, even in your model, the variances and the differences in the variances will shrink quite a bit. So the log transformation is very useful in reducing the problem of heteroscedasticity. Another additional advantage, of course, is that once you've done the log transformation, if you estimate beta 2 over here, beta 2 will actually give you an idea about the elasticity of yi with respect to xi. That is, it will tell you the proportionate change in yi due to proportionate change in xi. Whereas in the original model over here, it just tells you a simple rate of change. So that is another additional advantage that this log transformation has, and why it is very, very popular in empirical econometrics. Now, before I conclude this topic about the remedial measures, you should remember that even with these transformations, even though we do manage to either reduce the heteroscedasticity or actually resolve the problem, remove heteroscedasticity through these transformations, there could be a few new problems that arise, okay? Or there could be a few problems on how to go about the transformations. The first one is, what if you have more than 2 variable model? Okay, what if you have many explanatory variables? You might be confused as to which x variable should be chosen for transforming the data. Your best option then is to either run the Park or the Glester test or something of that sort to try and find which of the x variables are more correlated to the error term. That is your best bet. Then log transformation, like I said, is a very popular method of transforming the model to reduce heteroscedasticity. But if you have y or x values which are either 0 or negative, log of 0 and log of negative numbers is not defined. So doing a log transformation in that case is not possible. Then sometimes the problem of spurious correlation comes up. That is, in the original model, yi is equal to beta 1 plus beta 2 xi plus ui. Your y and x may not be correlated. But in your transformed model, you actually find that your y by xi is correlated with 1 by xi. So this can confuse you about whether the particular x variable actually has some sort of systematic influence on the dependent y variable. Okay, it could be that there actually is not much of a determining influence, but because of the transformation there is a spurious correlation that has come up, which will give us a misleading idea that this x variable has an important impact on the dependent variable. So one should be aware of that, and one should beware of that. Okay, then another word of caution you should be careful about is when your sigma I square is not directly known and you are trying to estimate the regression model using one or more of these transformation, the usual procedures that we used to use for hypothesis testing and inferences, that is the t-tests and the f-tests, all of them are strictly speaking valid only in large samples. So if you have a small sample and you have also done a transformation of some sort to reduce the heteroscedasticity, you should be careful as to how you interpret the results of your various hypotheses and statistical inferences. Because like I said, these tests are valid for larger samples and not so robust or not so reliable for small or finite samples. Right, so those are the problems that one must be aware of even when we do transformations to get rid of or control the level of heteroscedasticity. So again, with this problem of heteroscedasticity, some econometricians feel that it is only if the problem is very severe that you need to tamper with the data and go into making transformations of the original model. Different people, different econometricians have different opinions about that. The main decision should be made by the researcher based on the nature of the problem at hand and the purpose for which you're estimating your model. Whether it is just for making statistical inference, whether it is for making predictions or anything of that sort. So that concludes our topic of heteroscedasticity. Next, we will be discussing autocorrelation in the next lecture.